Hi everybody, it's been a while since I've done a video. Having kids means you have no time. This is a lesson I've learned. So we're going to do a quick one today on thyristors. Um, this is mainly aimed at the Year 11s doing their GCSEs, but towards the end of the video I'll tell you when. GCSE people, if you're bored you can stop listening, and there's some bits on the end that the Year 12s and Year 13s might make use of for the systems and control exam. So anyway, for GCSE electronic products, you need to know all of this stuff. How and when to use a thyristor, be able to spot the gate, anode, cathode, use and describe how it works as a latch, and then understand why it's an example of a bistable. And to do that, you've got to know what bistable means. So we're going to do all of that. We'll try and do it pretty quickly, and as usual, I'll show you some circuits that might explain it. So, alright, this is what I normally do as the starter to my lesson. So, what have all the following products got in common? This is what I get my kids to think about at school. Steady hand game, like a house alarm, your check engine light. Normally they can work it out. These are all devices that once they've been activated, they stay on, they stay locked on. Whereas the alternatives down here, a doorbell or a car horn, they only work while you're activating them, if that makes sense. So this is really to do with what thyristors do. They're devices that allow these things up here to happen, and you wouldn't typically find them on these sort of simple circuits. So that's gone a bit wrong. Anyway, so they are an electronic latch. What does that mean? Well, the easy way I remember that is, like, your parents might tell you, when you go out, put the door on the latch, which means you press that little black bit there once you pull the handle down, and it stops the little plunger thing from popping out and locking you out of the house. So you don't, so you can leave your front door open while you nip out to the car or whatever. You call that a latch. It's something you click on to lock something else on. That's the definition of a latch, something that locks on. And this is exactly all these little guys do, but in electronics. So the ones we use at school are called thyristors, and there are many ways in electronics of making a latch, but this is the one that they tell you need to know for your GCSE. They look like this. This is the symbol. The way I remember it is it's basically a diode, but with a third leg. So you've got, like a diode, you've got an anode and a cathode, as in a positive and a negative end, if you like. Current will only flow in the direction of the arrow, like a diode. However, they've got this third leg called the gate. If you're building a circuit and using this, the typical one we use in school that does most minor jobs is this one, the 2N5001. That's how you'd label the legs on that guy. Notice it's got a little flat edge on the case, so you know which way around to orientate it, okay? I never said this would be interesting. Right, on to the third bit before we show you some circuits, so that'll explain how it works. It's known as a bistable. Now, if you remember anything about 555 timers, I've done a video on those. You can get the monostable timer, which is a timer that will just make a single time delay. That would be known as mono because it has one stable state, as in its stable state is when it's off and not doing any timing. You might remember the astable circuit. That's the one that flashes back and forth. If you don't know what I'm talking about here, go and check out my video on 555 timers. You'll see both of these. So that has no stable states. It flips between the two. And bistable means it has two stable states, and we'll learn what those are: latched and unlatched. This is just general word play here that's good to know. Mono just means one, monobrow. Astable means, like, if something's agnostic, that means you don't believe in the religion of any kind or God. Bistable, bi means two, as in bicycle, biplane, and many other words I'm sure you can think of. So, moving on to the next slide. I could bore you with all this junk here. I could sit here and go, thyristor does that, only turns on when you put a voltage, whatever. I'm not going to bother. I'm going to show you it in a circuit. It's much easier to illustrate it. So, on to Circuit Wizard. Brilliant program. I'll repeat that. The program's called Circuit Wizard because I seem to get asked this on every single video. Made by a company called New Wave Concepts in the UK. I'm not sure if you can get it elsewhere around the country, but I'm sure they'll sell it to you. Don't try and find a dodgy copy. Pay the people. It's very, very good. So, anyway, this is the circuit. This is what it does. Very, very easy, really. I'll press play. Nothing happens at the moment. If I press this button here, the buzzer comes on. If I let go of the button, the buzzer remains on. That is the crux of all of this. It's a latch. This little guy here, the Thyristor, has caused it to latch on. And if I want to, I can press this button and reset it. Okay, to show you what's going on then, if we let's look at current flow first of all. What a Thyristor needs, and this is back to the PowerPoint, under normal conditions it does not conduct from its anode to its cathode. Here we go. I'm pressing play. Under normal conditions there is nothing going through the Thyristor. I've got red, which means voltage here, and green, which means 0 volts there. I've got no flow, if you like. Step 2, when a high voltage is present, only briefly, on its gate leg, it begins to conduct from its anode to cathode. So in our circuit, when I press this button here, it doesn't take a rocket scientist to see, I'm connecting the gate leg up to positive, and that's what you'd call high. So when I make that high, the transistor starts to conduct. Even when there's no longer any voltage on the gate, it will still stay conducting. That means it's latched, and as you can see, I've pressed that once, but I'm not holding it down, and it's still conducting. And onto the final bit, the only way to stop it being latched is to remove the power to the latch. Now, there are two ways of doing that. The first one is if I just turn the circuit on and off. Here, if I press this simple on and off switch, I am cutting the power to the latch. Therefore, the latch has been undone. However, you may be wondering, well, how does pressing the reset button reset it then? If I press that, you'll see it also unlatches. Well, this is just simple electronics here. When I press that button, I am making a short circuit around the Thyristor. Okay, so most of the current is taking the easier route back through the switch. Therefore, if most of it's going this way, the Thyristor is getting no or very little current. It's the same as being turned off. Okay, so shorting out the Thyristor basically has the same effect. So either of those two methods can be used to reset it. I'll leave that there in big, so there's a written explanation. You can pause the video if you want, and those of you who've got to write a report on this or whatever for a teacher can just probably copy and paste that and put it in. That's what most of you do, isn't it? Let's be honest. No one actually thinks of stuff on their own anymore. You just Google it, don't you? So if you need it, copy that down. So that's it. It's a device that locks on and latches. I've dragged that out for 8 minutes. I'm doing well. There's a worksheet. This is kind of, I'm just leaving this here for people's benefit really. This is the kind of level I think you'd need to answer at the exam. So explain in 4 steps. This normally I'd expect a 4 or 5 mark out of maybe 100 in the exam for this. So if you'd said step 1, pressing switch 1 connects the gate high. Step 2, the Thyristor begins to conduct, which means the LED lights up. Step 3 or stage 3, press switch 2 and this will short circuit the Thyristor, causing it to unlatch. Alright, if you can describe all those steps, happy days. Explain how pressing the switch resets it. Basically, if you could explain that short circuiting it, cutting the power, the same as if you had an on and off switch, you'll get some marks. Explain the purpose of the resistors, R1 and R2. They're here for protection, as nearly always with resistors. This is stopping the LED drawing too much current. This is stopping too much current going to the gate of the Thyristor. And then if you could draw the symbol and label it. So basically, if you can memorize that picture, anode, cathode, gate, and you can answer those questions there, for Electronics GCSE, you're pretty much there. It's 2016 as I'm recording it. This year's exam theme is, it was very vague, what was it? Oh yeah, games that test hand and eye coordination or something very similar. That's all they give you. So I think this is quite a likely circuit to show up, and I'll tell you for why. Let's go to Circuit Wizard and look at this. Those of you who go to my school, Collingwood, pretty much every secondary school in the country, if they do electronics, they probably built a steady hand game at some point. This tests hand and eye coordination. So this is why I think this could be a very likely circuit to come up. It's simple, it tests thyristors. I haven't seen thyristors in the exam for a few years now, so there's a good chance this will come up. But basically, if you take that switch that used to go in there and put one end of where that switch would be wired to the track, and the other end of where that switch would have been wired to the wand, the bit you move around the track, then if you touch the wand to the track, you make a connection, you trigger your thyristor, and the buzzer comes on. That would be your reset button. So for those of you at Collingwood, this was the circuit you made in Year 7 for the steady hand game. You probably didn't realise it because you were too small and little then to understand what was going on. Bless you. Remember when you all used to be cute? No, I don't either. Okay, let's have a look at some other circuits. So this is probably the last one if you're GCSE level that you need to bother looking at. And it's more an interest, and then for anyone on the internet who cares, I'll go on to a couple more here to show you some slightly more impressive things that can be done with them. So, right, you might remember decade counters. This is in the GCSE exam. This is a decade counter. Every time you send a pulse to it by pressing this button, just to show you, a pulse is high-low, as in red, green. On here, look, red volts, green, 0 volts. So every time you send a pulse to this thing, it counts through its next output. Alright, this is great, and some of you built this in Year 10 for your counter project, and I remember a few of you whining about how I want to make like a target game where I throw a ball at a dartboard and I hit the switch behind the dartboard, but I want it to count how many lives or how many times I've scored, as in every light that I win, and every time I win a new light I want it to stay on and stay on and stay on and stay on. So obviously when you've hit it 10 times you'll have 10 lights lit up. Now at the moment, decade counters, they don't behave like that. They just cycle through the outputs. However, with thyristors, you can achieve your dreams. Well, or at least something mildly impressive in electronics. So what I've done here, each output of the decade counter I've connected to the gate of a thyristor and then connected the LED to that thyristor. So if I press the button now and trigger the next output, the previous one stays switched on because the thyristor was latched. If I press it again, the next one comes on. Press it again, this LED will be on. However, none of these have thyristors, so you can predict what will happen. The rest of them, it will cycle through. So in your Year 10 reaction games or whatever, target games or whatever it is you were making, you could have put thyristors in to make it more complicated. Now, little truth here, the reason I didn't tell you you could do this in Year 10 is because, well, we're a state school in the UK. Our budget's about 50p, as you know well. These things cost like, I don't know, 30p each or something. So if I let all of you use 9 or 10 thyristors, it'd get pretty expensive. And none of you seem to pay any money for your projects, so that's why. I don't tell you so we can save money. Blame the government if you think that's a bit of a jip, but you'll have to deal with it. So you could use them for that. Now if you're Year 11, you can probably stop listening now and go away, watch a video again, do some revision. Right, for Year 12, or maybe Year 11 if you're keen and interested. Said no one ever. Here's another circuit that is just a slight adaptation of the thyristor, but shows how you could make something very straightforward but quite impressive as well. So this was a question I set as well. Draw a circuit using an infrared phototransistor, an LED, a buzzer and a switch, a key switch, that can be used as an alarm system that detects when someone enters a room. So just to show you that, this does that exact function. What am I doing here? Hold on. So this on and off switch is a key switch. You should have known these from your revision. Pretty straightforward. You can only turn it on and off with a key, so it's secure. This is a LED, an infrared one, and a phototransistor. So this is like a normal transistor but sensitive to light, so it's triggered by light. This is shining on here, a bit like a laser tripwire. That's why I've got that picture there. Now all the time light is shining on it. So imagine this is shining on here. This is conducting electricity through it. So electricity is taking the easy route, and therefore this leg here is what you'd call very low voltage. Okay. If I break the beam, I now make this thing block as a conductor. It won't allow anything through it. So this leg is now connected high. That triggers the thyristor, and even if someone walks out of the beam again, restoring it, the buzzer is still going off, and the only way to turn the siren off is to twist the key switch. Okay, so this would be a very simple intruder alarm. Um, and the key thing here is you need this on an alarm system. What good is a burglar alarm that only goes off while the kind burglar is standing in your tripwire beam? As soon as they step out of it and it goes off, that wouldn't be much useful, would it? So that's why we need a latch to keep it on. Okay, so that's one circuit you could make. This one's actually already in one of my other videos, the relays video, but this one's quite interesting. This shows how you can use a double pole, double throw relay as a latch, so we're not talking about thyristors anymore. What I've got here is a system that when the temperature rises above a certain level, do you remember my old analogy? Cold and dark in the basement, warm and sunny up top. If the thermistor's on the top, it's a warm sensor. Don't worry on internet land if you think I've lost the plot. That's one of my analogies for helping kids remember which way to put the components. But this will sense when things warm up, and when it gets to a certain volt, as it warms up, this voltage here will increase. At some point it will turn on the transistor. Transistor will turn on the relay magnet. The relay magnet will pull the switch across. This switch will allow the motor to turn, but this switch, and I'll show you the path, when it's active will allow the transistor to be bypassed, so the coil will be permanently powered, in effect latched, even when the temperature cools back down again. So just to show you that, raise the temperature up, the motor is turning, the coil is pulled across, and even if the temperature drops back down again, the motor stays locked on. And just to show you in current flow now, the reason that happens is because I've used the second switch of the DP-DT relay to take the energy that normally had to go through my transistor to make the circuit. Instead, I've taken it through this switch, which means I don't need this guy anymore. You're useless. My coil can now get its energy because of the latch. Okay, so you can use a double pole, double throw relay as a latch. This has been in the year 12 systems exam a couple of times, so it's worth remembering. So I guess this would be like a, I don't know, an emergency cooling system. So the first hint of something overheating, some emergency fan kicks in and keeps blowing. Or maybe a fire detection thing, like in a tunnel. You know, they have, like in tunnels that cars go through, they have those big fans to suck or blow air through the tunnel or draw air out of it, whatever. Fire alarm trips off, the fans turn on and keep turning as a precaution, I guess. That's the best I can come up with. Some of my circuits are completely useless. Right, the last one I wanted to show you was how you can actually make latches with NOR gates. Now, I'll do a separate video on this in the future, but it is possible if you take two NOR gates and wire the output of one of them to the input and the output of the other to the input of the other, that you can make a latch. So to show you this, just prove it works, press this button. That will cause the motor to start, and I've let go of the button, but it's still triggered, so it is latched, and I can reset it by pressing the other button. So this is quite a nice little circuit that Year 12 might like for their systems problems. Attach that motor to something. You could have a system where, I don't know, the motor turns and turns until it gets a certain distance along, and then the motor presses its own reset button and stops itself. Just a slight adaptation of that. All I've done here is put that on a relay, the old motor reversing circuit. Year 12 should recognise this. And this will now, this could be like a automatic camera pan and tilt mechanism. So if you imagine the motor's spinning one way until it eventually turns enough it hits a switch. That switch causes the transistor to turn on, flipping the relay, making the motor turn the other direction until it hits the switch on the right hand side, and then it turns back the other way until it hits the switch on the left, and then back until it hits the one on the right. And you can imagine So you can make a camera that kind of panned and tilted back and forth, hitting little limit switches. They don't have to be switches, it could be infrared beams, or it could be LDRs that go dark when it covers them up. Any kind of component here, right? But again, we're using the principle of a latch to do something in a circuit. I think there was a question about this as well in one of the exam papers, so that needed a kind of latching circuit. I think it was the rotating turntable one for a shop display, and it had to oscillate backwards and forwards through 270 degrees. There's your circuit, no pick chips, no nothing clever. Um, anyway, I've been talking about latches for 20 minutes now. That's more than enough. I'm gonna go to bed. So any suggestions, put them in the comments. Thank you very much for listening.